the last lecture by Jaeseong on towards Butler's conjecture. And on Thursday, we'll start a new series with Rosa Orlano. Okay, so anyway, Jaeseong, take it away.
Yep. Thank you. Thank you for the introduction. And thank you all for coming for the last talk. Today's talk will be short, maybe 30 minutes or so. Okay. So let's recall what we were doing. So for a partition view, we let the Schur expansion of this modified Macdonald polynomial, and we denoted the Schur coefficients by tilde k lambda mu, which we will call Qt cos-k polynomial. And the problem, the open problem, is to find the combinatorial interpretation. Combinatorial interpretation for these Qt cos-k polynomial. And Butler's conjecture is somehow she expected some nice behavior between these Qt cos-k polynomial, and Butler's conjecture may suggest that there might be a way, there might be a systematic way to anticipate new Qt cos-k polynomial k mu2 from old ones, so or known ones, mu1. Okay, so if mu1 and mu2 are two partitions that can be obtained by moving a cell or removing corners from one bigger partition. So here's an example. So this is a table for Qt cos-k polynomial where mu1 is 2, 2, mu2 is 3, 1. Okay. And as you see, the Qt cos-k polynomials, the sum terms are the same, like I draw with red arrows, and some of the terms are different, but they all have ratio q over t, which is t mu1 over t mu2. Okay, so some of it, and if we know which terms are the same and which terms are have ratio q over t, then, and if we know the Qt cos-k polynomials for this 2-2 shape, and then we can figure out what's the combinatorial formula for this Qt cos-k polynomial indexed by this partition 3, 1. Okay, so that was the philosophy. And and today I have attended a talk by Luc Lapointe, and I learned that actually Lynn Butler, she was a twin. So I just learned that it's like her conjecture. So half of Butler is here, and I don't know who is the mathematician between these two. Anyway, so using her conjecture or her suggestion, we may try to obtain some combinatorial formula. So for instance, so what's known? So we know that Qt cos-k polynomial indexed by lambda and one column partition, 1 to the n, is given by a generating function, e to the match of T, where T is over all standard tableau of shape lambda. And starting from this partition 1 to the n, by moving a cell one by one from the first column to the first row, we obtain hooks like I draw in here. And since we move a cell from the first column to the first row, all the consecutive two partitions are of the concerns of the Butler's conjecture. So if we let this partition mu1 and mu2, then their Qt-cos polynomial have obeyed the rule of the Butler's conjecture, and so on, and mu2 and mu3 and so on. So, and we know this Qt-cos polynomial for this partition, so maybe we can make a conjecture or theorem for the hook shapes. And what we found out is that Samia Saf, she wrote a paper in her 2018 paper, gave a combinatorial formula. For Qt-cos polynomial indexed by hook shape. And in our paper, in section 7.2 in our paper, we show that her formula is compatible with the Butler's conjecture. So we kind of simplified her formula because if you look at her paper, Samia Saf's formula, her formula involves some kind of bijections. And since our formula, since we have discovered that her bijections kind of compatible with Butler's conjecture, we don't have to follow all the way using her bijection. We just need the original permutation. We just need permutations. We don't have to follow her bijection. So we kind of simplified her formula. But today I'm not gonna discuss with this formula for the hooks, and I will focus on two column shapes. So like we obtained the hooks from the one column partition, we do the same thing. So moving cells one by one. We obtain two column shapes, two column partitions. Okay, like this. So starting from this one column partition, we move a cell from the first column to the second column, and we do the same thing for this partition to obtain this partition. And in this way, we can obtain all two column partitions. So we may want to follow this procedure and find which term changes in a combinatorial combinatorial interpretation. And until now, I have said that we are going to give a combinatorial formula for Qt-cos polynomial, but actually in this two column shape formula, we used K Qt-cos polynomial. So let me recall some terminologies. So K-short functions. Let par K be the partitions with its parts are less or equal to K. Okay. So the first part is K or less. So, and for a partition mu inside this par K, there is a family of symmetric function. S mu upper K, and this is a symmetric function of X, and it involves additional parameter T, which is called K-sure function. And I'm not an expert, and I know many experts are here, so I'm not going to go into the detail, but what I know is there's a conjecture of Luc-Lapointe, Lascaux, and Morse in 2003. It says that for a partition mu in part K, omega, this omega is an involution sending E to H or S to S lambda to S lambda transpose. Then anyway, omega H tilde mu is K-sure positive. And there's some progress. I mean, for K is equal to 2, Seung-Jin Lee have proved it, and K is equal to 3. Christopher Miller have proved it in his thesis. But for general conjecture, it is wide open. And a theorem, recent theorem of Blasiak, Morse, Anna, and Summers. They have a bunch of results, but they had proved that K-sure function is sure positive. So if we prove this conjecture here, or of Lapointe, Lascaux, Morse, then we will provide another proof of McDonald positivity conjecture. And since their proof, sure positivity is not just positivity, they gave a combinatorial formula. So if we can give a combinatorial formula for this K-sure coefficients, then we can give a combinatorial formula solving the open problem that I mentioned. Okay. And not just this, they have proved some nice properties of K-sure functions. One is shift invariance. So for L, which is big enough, so L is larger or equal to length of mu, then we can compute EL perp to the as mu plus 1 to the L, K plus 1. So K plus 1 sure function can be calculated by K-sure function, where a column is removed. So K-sure function of mu. So this is so-called shift invariance. And they proved the vertical dual Bieri rule. And actually, this is the main key to prove the sure positivity. And anyway, so ED perp of K-sure function is a generating function of t to the spin t, and K-sure function of inside t, and t is over vertical strong mark tableau K of shape d and weight mu. Weight d and shape mu. And I haven't defined the terms, this vertical strong mark tableau, spin, and inside. So it will be not very important in the rest of my talk, but I'm gonna recall it anyway. Okay. And you will soon realize what I'm talking about. So if you are not familiar with these notions, you don't have to be worried. Anyway, so there is a natural bijection between the set of k+1 core partitions. So k+1 core partition is a partition without a cell whose Fook length is k+1. And this is in bijection with k-bounded partition per k. Okay, and for example, if you consider this partition, like this, and the Fook lengths are like this. Oh, maybe I have to add this one. No. Okay, so maybe like this. The Fook lengths are like this. Okay, so this is 4 core, so 3+1 core partition. And the bijection kind of erase all the cells that has Fook length more than k+1. So like erasing all these, then you will have 3, 3, 1. So 3 cells in the first row, 3 cells in the first row, and 1 cell in the third row. And this is 3 bounded partition. And this is the bijection. And a strong cover from kappa is a pair of k+1 cores such that tau sits inside kappa, and by this map P, the size of P tau plus 1 is equal to the size of P kappa. So in the right word, their difference is 1 cell, and in the left side of the word, they are just tau is just inside kappa. And a strong marked cover is just a strong cover with a label on it, tau, kappa, and R. And here R should be one of the smallest row index of connected component of kappa minus tau. Okay? And one note is that if you have a strong cover tau from tau to kappa, then kappa minus tau, their connected components are all identical. Okay? I mean, we don't need to have that property for this definition, but yeah. And finally, a vertical strong mark tableau is okay. So, and this is VSMT of weight eta is a sequence. So T is a tableau, and T is a sequence from kappa 0, kappa 1, kappa 2, and so on, and kappa M, and they have labeling, or they have markings. So RM. Okay. And these markings R1 through RM have to satisfy R1, R2, R eta 1. R eta 1 plus 1 is smaller than R eta 1 plus 2, through R eta 1 plus eta 2, and so on, and so on. Okay. Okay, so such that. And we denote the set VSMT K mu, no, eta mu to be the set of vertical strong mark tableaus T of weight eta, and outside, I haven't defined outside, but outside is P kappa M is mu. Okay, so the last K plus 1 core is associated to mu via this bijection P. Okay, and the inside is P of kappa 0. Okay? And inside T is P of kappa 0. Okay? And finally, spin of a strong marked cover, spin tau kappa R, is given by formula C times H minus 1 plus N. And here C is the number of connected components in kappa minus tau. And H is, as I said, each connected components are identical. So H is a height of a connected component. And N is a number of connected components higher than this marking R. Okay, so there's a way to give a spin statistic to this vertical strong mark tableau, and strong mark cover, and we define spin T to be the sum of it. So sum of spin of kappa I R I plus 1 kappa I plus 1. Okay. So this is it. So these are the definition of spin inside and vertical strong mark tableau. So this by this vertical dual Berry rule, there's a way to obtain this. There's a way to expand this E perp to the K-short function into the positive expansion of K-short functions. And as I said, if you are not understanding what I'm saying right now, these notions, you don't have to, because for our purpose, we only concerning two column shapes. So and one column shape Macdonald polynomial, its omega image, it's known to be one short function of the same partition. And by shift invariance, we know that this is En perp to the two short function of rectangular shape 2 to the n. And by using vertical dual Berry rule, we know this can be expanded into VSMT to weight n and shape 2 to the n, t to the spin t, and as two short function of inside t. So what we have to do right now is to find out what are these vertical strong mark tableau of this weight and shape. And this is it. So I draw some pictures, and starting from this is 2 to the n. So starting from this, these paths, like all the way to the bottom, each path represents a vertical strong mark tableau of this weight and shape. Okay, so there are 4 passes, so P1 through P4. So by this formula, we can conclude that omega h tilde 1 4 is sum of all paths and t to the spin of the path and shape of the end vertex of this path. Oh, and spin p, I have written spin statistic for each strong marked cover. So this spin p should be the sum of these labelings, okay, in the path. And this will give t to the 4. So this path has spin 4. So t to the 4, 2 short function of 2, 2. And for path P2 and P3, it's t to the 3 t squared times as 2 short function of 2, 1, 1. And 1 times 2 short function of 1, 1, 1, 1, which correspond to the last path P4. And what our formula is suggesting is that to obtain the 2 column shape 2, 1, 1 from this 1, 1, 1, 1, what we really have to look at is if it takes a left turn or right turn. So, and if a path takes left step in here, you multiply that by the right ratio, and if a path take a right step in here, then you just leave the turn, leave the spin statistic. So what I mean by that is, okay, so I'll erase this. Okay, so starting from, oh, so this is the 2-short expansion of omega h1111, and since the path P1 and P3 takes left turn here, so okay, so P1 should be changed by Q over T, and P3 has to be changed by Q over T. And this is equal. So the stat will be Q T3 and T to the 3, QT and 1. Okay. And to obtain 2 column shape 2, 2 from this 2, 1, 1, we look at this second like here. So once again, if a path takes left turn, we multiply the turn by a right ratio, and if we take right turn, we leave the turn. So P1, oh, sorry. This is wrong. Here P1 and P2 took a left step, right? So it should be like this. P1 and P2 is changed, and this one is equal. Okay, and in the second step, P1 and P3 got left, uses left step, so they changes by, oh, so sorry. This is Q over T to the 3. So it's QT and it's Q, okay? And this ratio is Q over T. And these two are the same. Okay, and this will be Q squared, this will be Q, this will be QT, and this will be 1. So this is how our formula gives a two-short expansion for Macdonald polynomial indexed by two column partitions. And the reason why I choose to introduce this formula, I mean, this formula is very works for very small examples. So our formula works for hook shapes and two column shapes. So, but I believe there's a way to, maybe there's a way to extend our formula, because one naive guess is, so starting from one column partition again. So this is one short function, and applying shift invariance twice, what we obtain is three short functions of rectangle, three column rectangles applied by E and perp twice. And by applying vertical dual Bieri rule, then we can obtain a three short expansion of this this function, okay, or this one. So what we have to do is basically starting from this three column rectangular partition, we applied vertical strong mark tableau. I mean, we recalled all the vertical strong mark tableaus while applying E and perp to obtain a similar picture like this. And we, once again, we apply E and perp to obtain something like this. And the resulting partition, or the endpoints of each path, will be sit inside part 3 and of size n, because we have applied E and perp twice. So from this picture, we can write down omega h1 to the n by a sum of paths and sum of spin t, I mean spin p, and three short functions of endpoint of the paths. And maybe there's a way to characterize the paths while we obtain new partition mu from the old partition mu1, and characterize a paths like this. So we have characterized the changes by checking if the path uses the left step or right step in this picture in the two column case. So maybe if we draw this diagram and characterize the paths to give a three short expansion to three column Macdonald polynomial. So we haven't we have, to be honest, we have tried this and we find it difficult to find a pattern, but maybe there's a hope. So I wanted to introduce our ideas, and this is all for today and or for my lecture series. And I'd like to express my gratitude to organizers Jim and Anna to invite me here, and thank you everybody for coming, and those who are watching in YouTube. Thank you.
Oh, very good. That's oh, by the way, Lynn is the one on the right without.
Okay. So she's mathematician. Thank you.
So any questions for Jaeseong? So what led you to have the idea about the K-sure? Just seems like it's totally different from the Sammy Asaf and all that.
Yes, it's very different from her formula. Oh, and I had to mention that this formula actually, I mean, we had another motivation. I mean, we tried to exploit this shift invariance and vertical dual variable, and then we made some observations. But this formula is actually equivalent to, I have to mention this here. So this formula is equivalent to Jaeseong's formula. But Jaeseong, in his, maybe his first paper, yeah, he had some combinatorial formula for two-column McDonald polynomials, and his formula is equivalent to ours. So yeah, so we haven't proved nothing in our paper. We proved the equivalence, and yeah, Jaeseong did all the work.
Any other questions?
Actually, I want to know, you said you tried the 3-column case, and I know that I think Jonah has the 3-column case, right?
Oh yeah.
Jim, if I'm correct, right? So like, how would this idea and his result match, or is like very different or something like that?
Yeah, I think, I mean, first of all, we don't know this idea makes sense or not, but anyway, and we have checked Blaszczyk's formula, and it is not obviously compatible with Butler's conjecture. So
In fact,
we have to make
two-column-
another.
So there's a two-column rule that is in our paper, the original paper with Mark and Nick Lohr, for 2 columns. And Jonah's 3-column rule generalizes that. But
Okay.
even the 2-column rule, we don't know how to do that with Butler's
Okay.
conjecture.
I see.
So, yeah.
Yeah. So to make Butler conjecture compatible formula, we need to find a new formula in some sense.
Yeah. Okay, well, thanks for a great series, Jaeseong. And yes, let's give another round of applause for those excellent lectures. Yeah, very good job. And again, on Thursday, we'll start a new series connected to representation theory. So I guess Anna sent out a email about that.
Yep, everyone will receive an email tomorrow on like the time and then the abstract of the talk series.
All right. Aloha.
All right. Thank you so much. Bye.
Thank you. Thank you. Bye bye.